Okay, so what I'm talking about today is a little more of focusing on how do we practically use all of the science that all of you guys are developing. And I'm going to give some specific applications and talk about what we're doing in the US with regards to hydrogen embrittlement and some of the new work that we're doing in it. And so this is a combination of a few different companies that have been working on this: US Corrosion Services, which I'm representing, and then also Schlumberger and Applied Fracture Mechanics. The point that I want to bring about today is how do we practically take what we're doing in academia and in research and apply it in a way that we can really fundamentally change the way that people are actually using materials. Okay, so I'm going to describe a paradigm and then also talk about what we're doing to implement that in the US. So the first thing is measure and understand the susceptibility of your materials and understand the fracture toughness and use fracture toughness related techniques. The second thing is once you've done that, then you can select materials that you know are safe based on the testing that's been performed. And then the last thing, I love this one. This is from ChatGPT, this hilarious little guy. And of course, they misspelled embrittlement, is to prevent problems by not only selecting materials that are good, but even when you select a material that you've tested and you know it's good, that doesn't prove that on a batch per batch basis it's good. So the next step is implementing quality control and potentially even non-destructive testing techniques that'll allow us to catch materials before they get out into service. So the fundamental idea that lies behind all of this is something that has been used in a lot of different industries, which is the idea of leaking before cracking. Because if you have a leak, you can safely go and prevent it. If you have a large crack that becomes catastrophic, that's when you have much more dangerous failures. Okay, so I'm not going to have time to go into all the details here, but if you're interested, I'm happy to talk about any of the details of these slides. I have 20 to get through in about 12 minutes, so I'm going to cruise pretty quickly through these. But this is the fundamental fracture mechanics that goes behind it to say whether you or how you design your materials and pick them so that they will leak instead of cracking. Okay, and so this approach that we're using right now is similar to what's been used for sour service for a long time. So in the US, we started with MR0175, which is the materials requirement for sour service. That was implemented back in 1975 and then has been steadily added to over the years. And if you've seen it now, it's a massive document compared to back in the day when it only used to be a few pages long. But that's because we've implemented all of the learning and research that people have done in sour service. And so what's happened is we developed test methods. Those test methods are required for batch testing of every batch of material that's going into critical sour service applications. And then we also have an ISO method that's been developed as a corollary to go along with the method that was developed by previously NACE and now AMP. And we're doing the exact same thing now for hydrogen embrittlement. So we started with first with a technical report that laid out all of the research that's been done. Based on that technical report, we're developing the MR, which is the materials requirement, the materials that are allowed, as well as what testing needs to be done. And oops, this is going to change. It should be TM 21546. So that's a typo on my part, but that'll be the new test method that's coming for hydrogen embrittlement. And these question marks are here because we haven't developed the ISO method yet. But that's one of the corollaries that I'm probably going to be working with a lot of you on, hopefully, is developing something to go along with what we're making at AMP. So going back to leak before break, this is the concept. And what I'm showing you here is the crack length that's acceptable so that you can have a leak before you have a failure. And if you get beyond this point, you get to the point where you get into the global failure region. This is the problem you want to avoid, okay? And so down here, we're talking about a leak detection system. And the leak detection system has to have some testable crack length. So if your crack length is so small that your test method can't find it, that's a problem. And that's part of what we're developing as part of this methodology is test methods with crack detection methods that are small enough to find the problems before they lead to catastrophic failures. So this is the engineering approach. We're looking at, in this case, we're specifically focusing on subsea operations. And part of the impetus of that is that there's been a lot of failures related to hydrogen embrittlement in subsea operations. So we're developing a test method that's focused on materials that are typically under cathodic protection and using an EAC type of fracture toughness evaluation. So this is applicable to hydrogen embrittlement, but also equally applicable to a lot of other environmental types of cracking mechanisms. Sorry, and the last thing is doing batch testing. So the same kind of methodology that's being used in sour service, where you test every single batch, we're developing something that can be tested quickly enough that you can do the same thing for hydrogen embrittlement. Okay, so in our case, we're measuring the susceptibility and doing our fracture toughness evaluation using two main methodologies. One is the step loading and the other is SSRT. They both have advantages and disadvantages, but both of them give you a lot of data at a fairly quick time frame. One of the things that we've had to come together to agree on, though, is if you're doing slow strain rate testing, there is definitely a sensitivity of your strain rate. And so we're settling on only specific strain rates so that we can eliminate some of that variability. Okay, and then once that's done, those will be implemented into the new test method, which is going to be this one, 21546. And then as well, we're going to have material requirements. So as you can imagine, in the first version, we're going to have a limited number of materials that are already known to be relatively safe, and also a methodology for how to test new materials. So for example, if you're making an additive manufactured version of something that we already considered safe, this methodology will allow you to prove that those different additive manufactured materials or new alloys that are developed are capable of doing the same good performance that we expect from other materials that we already know and use. Okay, and then all of that will allow us to implement that into the quality control programs that everyone is doing so that when you're buying materials, you can test them quickly. And then the QC testing is going to be have requirements that are developed and specific for each of the materials that we're working on. So this is an example of the step loading test. This is one that we use a lot, and I personally like it because it's been proven to work really well to correlate between small samples as well as with full-scale samples. And it has a lot of different uses in hydrogen embrittlement. You can use it for quality control testing. You can use it for initial characterization and comparison of alloys. We also use it for failure analysis and forensic investigations. And here's an example of the difference between this and the old school methodology. So typically in a lot of cases, we're using sustained load testing, and the sustained load test is written into tons of old standards across many different industries. But especially in aerospace, we see sustained load testing being used all the time. I'm personally against that because I feel like with sustained load testing, you're only getting a pass-fail, and it takes quite a while. So in this case, this is an 8-day test. But once you include machining, setup, takedown, data analysis, typically you're looking at 2 to 3 weeks to get your test results. And in comparison with the step loading, we can get the same results in 1 day. For softer alloys, this might be 2 days or 4 days, but still it's a pretty quick test. And the other thing is it's quantitative. So wherever you end up finding the threshold, that's an actual number instead of just a pass-fail at 75%. Okay, so these are some examples of areas where we're using it in comparison of plating and coatings. That's a critical one because those have a large effect, which I'm about to show you in a minute, as well as for exposure to chemicals. So one of the things that we forget about is that it's not only how the material's produced and what the environment could do to it, but also what kind of chemicals is it exposed to. And one of the big ones that can be problematic is actually cleaning chemicals. They can induce a lot of embrittlement. And then we're also using it for research and development, looking at how hydrogen embrittlement is affected by things like galvanic and crevice corrosion, as well as failure analysis. So here's an example looking at the OCP of coatings and how this affects their hydrogen embrittlement performance. And what I'm showing you here is kind of a complex chart, but we have 3 different strength levels of materials. Each of these strength levels of materials, these are all steels, were coated with these different coatings. So we have hot dip galvanized, zinc nickel, dacrymet, magni, flake zinc nickel, titanium cadmium. And then what I'm showing here is the susceptibility ratio. So the susceptibility ratio is essentially a way of understanding how much the material was affected by embrittlement. And the lower you are, the worse your performance is in embrittlement. So typically the acceptance criteria is set right at 1.2. And what you can see here is in these high strength materials, there's only a handful of coatings that are actually acceptable. And I would consider all the rest of these to be problematic on something at this high strength level. As you go to more medium strengths, you see a few more of these that start to be close to or in the acceptable range. And then once you drop down to 36 HRC, we actually see that all of these coatings turned out to be acceptable, or at least above the minimum acceptance criteria. So here's an example of looking at the effect of the potential and how different potentials work as well. So as part of this test methodology, we want to understand what happens if you have either an impressed current or if you have anodes. And depending on the current that your material is actually seeing, you have a huge impact on the crack growth rate and essentially on the embrittlement susceptibility. Okay, so the advantage of this kind of test is it's very accurate. The disadvantage is these kind of tests can take months to complete. And so in a practical time frame, it's not that helpful for someone who wants to buy material and test it and get it shipped out the door right away. And then in comparison, we can do sort of similar things, with the step loading, but in this case, we can complete and get our data from the same kind of alloys within a much shorter period of time. So within a matter of a few days, you can have your results. And so this is an example of why this testing is important, is when you're looking at cathodic protection, especially when you're using anodes, you find that depending on how the anodes are loaded, you might end up with some anodes that are almost completely depleted after 20 years, other ones that never even activated correctly or have calcareous growth that's causing problems with it. And so that was part of what also pushed us to do more of this research and development. So I'm not going to have time to get into it, but we've done a lot of research on the coating breakdown factor, which is one of the effects that allows you to understand how your coatings break down over time. And based on that, you can calculate what the anode loading needs to be. And then I'm going to talk about a few recent advances of things that we've been working on. So one example is looking at fatigue cracking. One of the things that step loading can be helpful for is determining the initial threshold for fatigue cracking. So instead of just running a bunch of long fatigue tests and then looking at your data and going, okay, here's the point where our threshold is, we're doing step loading with fatigue so that we can determine a threshold and then focus in on that area more with more traditional step fatigue tests after that. Another area that we're working on currently a lot is temperature effects. Well, a lot of the step loading and other hydrogen embrittlement research is done at room temperature. But what we find is for different materials, there's high and low temperature effects that are both interesting and really informative, because in some cases the embrittlement goes away and in other cases it becomes worse. And then the last one is the accelerated testing. So it's already an accelerated test, but for quality control purposes, you can determine a material and determine the initial threshold by doing your testing. And then say, for example, that let's say you determine 70% as an acceptable threshold for you. We've been doing research to show that if you do your initial loading correctly, you can jump up to within 10 or 20% of that threshold and then start doing your step loading and cut down the amount of time substantially further. So what that means is instead of the test taking 20 hours, you might be able to complete it in 6 to 8 hours. And that's perfect for industrial production because you want to be able to have answers the same day or next day. So by the time you're finished making a part, it's ready to go out the door. And one last example is using step loading for stress corrosion cracking. So it's also very effective at evaluating and measuring and developing thresholds for stress corrosion. And with that, I'm going to, oh, here's the end. So basically what I've tried to present is what I think is a practical way to apply hydrogen embrittlement testing and specifically the step loading test to focus on developing materials and getting them out into service safely in a fast time frame. And if you're interested, I'd love for you to contact me to learn more or to participate in the development of these new standards. Thank you.